Hi, this is Module 43 of Mechanics of Materials Part 1. We're going to look at statically indeterminate structures in this module. And so our learning outcome is to actually solve a statically indeterminate structure problem for axial loading. And so here is our example. Please realize as I go through today's module, this is going to be a little bit longer video module than normal because for continuity, I want to get all the way through the problem. And if I cut it up into different modules, it just wouldn't flow as well. And so we'll go through it a step at a time. Bar DE here is aluminum. I give you the cross-sectional area, the modulus of elasticity, and what the yield stress is for aluminum. And I do the same thing for bar BC, which is steel. I got the cross-sectional area, the modulus of elasticity, and the yield stress. Now we're going to consider bar A, B, D, F to be rigid. Both the aluminum and the steel bars are going to be deformable. And we're also going to neglect the weight of the bars, and that's because they're going to be negligible. The weights are going to be negligible compared to the forces that they are supporting. And so we're asked to find the axial stress in the aluminum and steel bars and the deflection at point A. So we will also work, just for simplicity, I'm going to work in units of kilonewtons per millimeter squared and GPa, gigapascals, because 1 gigapascal is equal to 1 kilonewton per millimeter squared. You can change those after you get your final answer, but it just helps to use consistent units. So my question to you is, what should we do first? And what we're going to do first is to look at the static equilibrium of our system. And so how would we develop the static equilibrium equation or equations for our system? And what you should say is what we've been doing from my very first course, which is to draw a good free body diagram. And so I'd like you to draw a free body diagram for this structure. And the body of interest now is going to be our rigid bar A, B, D, F. Okay, here's what your free body diagram should look like. This is point D here. So here's my free body diagram again. You'll notice that this is what we call a statically indeterminate problem because we have 3 independent equilibrium equations, as we've known since we've started the course and my earlier courses, but we have 4 unknowns, Fx, Fy, the force in D, and the force in B, the axial forces. We don't have any Y components at D or B because the aluminum and the steel bars are 2 force members. And so here are my unknowns. So I'm not so happy. 3 equations, 4 unknowns, statically indeterminate. And so, but let's start by at least writing the best equilibrium equation we can to start to solve the problem. And so what would that equation be? And what you should say is, well, let's go ahead in some moments about point F because I'm really not interested in Fx and Fy, at least in the problem statement. I'm interested in the axial stresses in the steel and the aluminum bar. And so by summing moments about F, I won't have to worry about these unknowns and I'll just include the unknowns that I'm interested in. So go ahead and do that moment equation on your own and come on back. And so here's the equation. Now I have one equation. I've reduced this to one equation, but I have 2 unknowns, okay, B and D. And so here's my equation of equilibrium, 1 equation, 2 unknowns. We're going to need an additional equation to solve these statically indeterminate problems. And so what we use is what's called the deformation equation, which looks at the geometry of the deformation of the members in the structure, and it's also called the compatibility. It can be called the compatibility equation because it enforces compatibility between the equilibrium and the deformation that the structure undergoes. And so we're going to assume small deformations, and so therefore small angles. And here is my rigid bar in its original position, and then I'm going to exaggerate so I can see the deflections, but here it is as I move to the right. And so I have a deflection at D and I have a deflection at B. And I want to go ahead for my deformation or deflection equation or compatibility equation to relate those deformations. And so I'm going to have, by similar triangles now, the deformation of D is to 300 as the deformation of B is to 600. And so what I find out is that 2 times the deformation at D is equal to deformation at B. And so that's my deformation or compatibility equation. So here we are. We've got our equilibrium equation. We've got our deformation equation. But we don't know where are we on the stress-strain diagram for what's happening to our steel and our aluminum bars. And so we'll go ahead and use that idealized elastoplastic material assumption. And since I don't know if these bars are in the elastic or the plastic region, I'm going to have to make an assumption. And so what I'm going to do is I'm going to assume that we're in the elastic region, the linear elastic region. And if we're in the linear elastic region for prismatic bars, we know that the deformation is equal to PL over AE. We developed that in the last class. In the linear elastic region for this prismatic bar, delta is given by this expression. And so I've got 2 times the force, the axial force in D is going to be D. And its length is 250. And we're going to divide that by its area, which was 5,000, times its modulus of elasticity, which is 70. And that has to equal the deformation at B, which is equal to the force B times the length of BC, which is 250, divided by the cross-sectional area of BC, which is 1,300, and the modulus of elasticity, which is 200. And if we go ahead and solve then for B and D, we end up with B equaling 1.49D. And this is going to be equation 2, because now you see that I have 2 equations, the equilibrium equation and this equation, with 2 unknowns. The force in member C and the force in member DE. Okay, so here's those 2 forces. Okay, solving simultaneously. Remember, we're still assuming that both members are in the linear elastic region. We got to check that to make sure that that's true. And so let's first check the aluminum bar to see if it's in the linear elastic region. And so I've got sigma DE, which is the stress in DE, is going to be equal to the normal force, which is D over the cross-sectional area. The normal force in DE, we found, if we use this assumption, is 446 kilonewtons. And we're going to divide by its cross-sectional area, which was 5,000. And so that gives me a stress of 0.0892 GPa, gigapascals. But we find that 0.0892 gigapascals is indeed less than the aluminum's yield stress, which is 0.28 GPa. And so this is good. We'll have a smiley face here, because this means that my linear elastic assumption for the aluminum bar is correct, and it holds. I want you to do the same thing now on your own for the steel bar. Find out what the stress is for this assumption in the steel bar. Okay, so you develop, again, sigma in the steel bar is equal to the force in the steel bar, the axial force divided by the area, and this is the stress. But we see that this stress now is greater than the yield stress, so that steel bar is not going to be able to hold that much stress, and so that's not okay. The steel bar has yielded, so we're going to have to go back and rework what we've done. And so here's our equilibrium equation. We know that aluminum is in the linear elastic region, but the steel has yielded, and we're going to say that it's in the perfectly plastic region for the elastoplastic assumption. And so now we can find the axial stress in the steel bar, because we know that it's going to have a stress that's equal to the yield stress, or 0.25 gigapascals. And so we've got 0.25 gigapascals or 250 megapascals is all that the steel is going to be able to hold. Okay, so there's my equilibrium equation. I found the stress in my steel bar. Now I want to see how much force that steel bar is actually going to be able to support, given that it has yielded. And so we'll use this stress definition again, and I'd like you to go ahead and calculate what that force is that can be held in the steel bar. And what you should say is, okay, the force B is equal to sigma times A, and sigma is the yield stress, A is the cross-sectional area. So what we see now is that the steel bar can only hold 325 kilonewtons. When we had the linear assumption back here, we said it would hold 664 kilonewtons, but it couldn't hold that much. And so it's 325 kilonewtons. I can put that into my equilibrium equation and see now that D, the force that's got to be held by the aluminum now, is more. It's going to have to be 675 kilonewtons. And so I find that my stress in my aluminum bar has now gone up. It's going to be 0.135 gigapascals or 135 megapascals, and it's going to be in compression, right, because we're pushing on it to the right. But we know that the yield stress of aluminum is 0.28 GPa, so we're still in the linear elastic region, and so we're good to go. And so that's our answer for our aluminum bar. So we now have found both the axial stress in the aluminum and the steel bars. What we want to do finally is to calculate the deflection at point A. In calculating the deflection, we must use the aluminum bar because that's the only one that our deflection calculation delta equals PL over AE will hold. And so there's our DL over AE, and so the deflection in the aluminum then, deflection in the aluminum is going to be the force in the aluminum bar, which is 675, times its length, which is 250, divided by its area, which is 5,000, and E, which is 70. And so it ends up coming out to be 0.482 millimeters. That's the deflection of the aluminum bar. And so knowing that, we can now come in and we can look at the deflection at point A. We know what the deflection of D is. We just found it. Because the aluminum was still in the linear elastic region, I want to find the deflection of A. How would I do that? Go ahead and try to do that on your own. And all we do again is use similar triangles. So I've got the deflection at D is equal to, over 300 is equal to the deflection of A by similar triangles to 750. And so the deflection at A then is going to be, if you calculate that out, put in your value of 0.482 here. The deflection of A ends up being 1.205 millimeters. And so we've solved our problem. Okay, so that's a good statically indeterminate problem. You should try some on your own. Find a reference where you can go through either online or in a textbook, and practice will make perfect. But they're rather long problems, but they're straightforward if you go step by step. And this is a very typical example. So that's it for today's module. See you next time.